Hello, welcome back folks. So today we'll be looking at the properties of fields. In the last video I introduced some definitions, that is the closure, commutativity, associativity, identity, inverse and the distributivity, and these six rules of fields, if you will, are what define the the concept of field. Yeah, that's better. And the properties I have defined over the properties I have written down over here are, well, kind of like FAQs, frequently asked questions, if you will. Now, the first of them is a times 0 is equal to 0, and this holds for any a belonging to the collection of elements f. Is this true for any field? Well, turns out it is. And how is that happening now? Let's see. We haven't exactly mentioned that a times 0 can be 0. A times 1 can be 1, but a times 0 is 0. Well, that's the beautiful beauty of fields. It gives rise to such properties like this. Now, let's see how it's done. A can be written as a times 1. This is by the definition of multiplicative identity, and therefore by the property of additive identity, that is by the definition of 0, this 1 can be split into 1 plus 0, and that 1 plus 0 times a can be split into a times 1 plus a times 0, and this is by the distributive property. And note that the LHS is still a. The RHS is what we are manipulating. Now a times 1 turns out to be a again, that is by the definition of 1, and this a times 0 is, well, it's just there. Now add the additive inverse of a. Now by definition the additive inverse will always exist for any a, and so we can add that to both sides. That is the equivalent of cancelling the a, and this will result in 0 and 0 over here, and 0 added with anything will result in the same. And so a times 0 is equal to 0, and that's how we prove it. In the real numbers and the complex numbers, we actually took this property for granted, but when we define them, when we look at them from the lens of fields, this property is not exactly, well, it's not a given. It can be proved, but it's not a given. Similarly, the property that minus 1 times anything will give you the additive inverse of that thing. This is also something that we took for granted again. And these sort of manipulations, well, this is what makes it an algebra, right? This is what makes this course an algebra course. It's precisely because of these sort of manipulations that we do to prove all these interesting properties that makes this thing called linear algebra. Okay, so moving on to this. Now 0 can be written as 1 plus minus 1, definition of additive identity. Therefore, if we multiply sum a on both sides, then a times 0 is the same as a times 1 plus minus 1. Distribute it and you will get a times 1 plus a times minus 1. The LHS will reduce to 0 because we just proved it a few seconds ago. And now this 0 can be written as, this a times 1 will reduce to a times minus 1 will just sit there, add minus a to both sides. So I mean, till here we can just say that by definition of an additive inverse, this a times minus 1 has to be the additive inverse of a, since when it's added to a it gives 0. And now if we add minus a to both sides, since we know that minus a will exist, we can mathematically show that minus a is the same as minus 1 times a. Alright, we'll also show that this minus a and also the multiplicative inverse, whenever it exists, they are unique. So the inverses, whenever they exist, are the inverses. Okay, there is not multiple inverses, there is only one inverse, and it's the inverse. Okay, the next thing is 0 unique? Well, it sure is. So it is the 0. Suppose we have two additive identities, 0 and 0 dash, then 0 plus 0 dash, it can equal 0, right? By definition, 0 dash is the additive identity, so anything added to it will result in the same again. But similarly, 0 is also an additive identity. Um, so anything added to 0 will result in the same thing as well. And so by this, 0 and 0 dash are one and the same. And with that, I have shown that 0 is unique, it is the 0. And similarly, 1 is also unique, and it is the 1. It's not a 1, it's the 1. Similarly is minus a. Yeah, I already told you that this will be unique, and this is the proof of that. So if there are two inverses, a1 and a2, a plus a1 is 0, a plus a2 is 0, by definition again. So let's do some mathematical manipulations over here. Look at this. a1 can be written as a1 plus 0. Cool. Okay. Now 0 can be written as a plus a2. By associativity, this thing, the parentheses can be moved. So a1 plus a, that reduces to 0, just like this. And you have a2 over here. And the LHS all the while has been a1. With that, we have shown that a1 is a2, but a1 and a2 were the additive inverses of a, but both of them turn out to be equal. And so we have proved that minus a, that is the additive inverse of a, is unique. Similarly, this a raised to minus 1, which we used to denote the multiplicative inverse of a, that is also unique. And I'll leave you to look at the proof of that by yourself. And also, I highly recommend that you guys write the proof by yourself. Don't just listen to me. Write down the proof, verify each step, and well, understand how this proof has come about. Okay? Gain some insights into what sort of algebraic manipulations I have been doing all along. Those things are not, something that is general. That is just something you figure out on your own. All right. This is where some of the good results come in. And are there any fields where 0 does have a multiplicative inverse? In the definition, I already mentioned that 0 does not have a multiplicative inverse. Have you ever wondered why? I mean, okay, in real numbers, 1 by 0 does not exist. We cannot divide anything by 0, but that's going by just one particular example of a field. So why exactly does that apply to all fields? That's what this proof is going to be about. Does 0 even have a multiplicative inverse? Is there any chance that it does? So suppose it does, let's say. We'll call that 0 raised to minus 1. So 0 times 0 raised to minus 1 has to be 1 by definition. But we have also shown in the first property that anything multiplied with 0 is 0. And so that's why 0 equals 1. But that's not true. That's not even possible actually. 0 cannot equal 1. 0 will never equals 1 in fact. And that's what the next proof is about. Yes, I should have put this above, but can't do anything about that, can I? So can 0 equal 1? Answer is no. Obviously it cannot. But from a more general point of view, let's see how. If 0 is equal to 1, let's multiply some element that is not 0. Please, not 0. Mind that. So a times 1 is a times 0. A times 1 will reduce to a. A times 0 will reduce to 0. And that will give you a equals 0. Which is exactly what I said was not true. Because I have already chosen a as something that is not 0. And with this contradiction, I have shown that 0 cannot be equal to 1. And hence, there cannot be any field where 0 has a multiplicative inverse. Not possible. So from this property, actually there's a pretty slick theorem that states that if there is a field f along with addition and multiplication, then it must contain at least 2 elements. And the smallest field that contains 2 elements associated with a modulo 2 addition and a modulo 2 multiplication is called the Galois field 2. So Galois field is it's a special type of field. Read up about it. I'll probably actually do a video on it in the future, but the point is this Galois field 2, it only consists of 0, 1 as the objects, and associated with that is the modulo 2 addition and multiplication. So this is how it works. 0 plus 1 is 1, and modulo that with 2, the remainder is 1. So 1 plus 1 is 2, so 2 remainder, the remainder when 2 is divided by 2 is 0. And similarly 0 plus 0 modulo 2 is also 0. So similarly there is also the modulo 2 multiplication, that's 0, 0 times 1 modulo 2 is 0, 1 times 1 modulo 2 is 1. And please verify that this field over here, the Galois field 2, is actually a field. Please, that's an exercise. Go and verify it. Be familiarized with the definition of fields. Okay, in the next video I'll give you an example of fields, and with that I'll end the video here. Stay tuned for next time. Thank you.